Hey, welcome. Today, we're going to crack open the machine learning toolbox. You know, ML isn't some kind of dark magic, not at all. It's really just about understanding what your problem is and then picking the right tool for the job. And trust me, by the end of this, you'll know exactly how to pick the perfect one.
So here's the roadmap. First, we'll get on the same page about this whole toolbox idea. Then we're going to dive deep into the three main jobs a machine learning model can do. You've got predicting numbers, sorting things into categories, and, my personal favorite, finding hidden groups you didn't even know existed. And to wrap it all up, I'll give you a super simple guide to make sure you choose the right tool every single time.
All right, let's get into it. First up, the right tool for the job. Let's really explore this idea of a machine learning toolbox.
I mean, have you ever really thought about it? How does an app on your phone have any clue what a house is worth? Or how does your inbox just know that an email is junk? It's all powered by machine learning. But the real secret isn't just using ML. It's about choosing the right kind of ML. And that's what we're here to figure out.
So here's the absolute key. A model is just a fancy word for the specific tool, the algorithm you pick. And you pick that tool based on the job you need to get done. Is your job to predict a price? Well, that's one kind of tool. Is it to decide if something is spam or not? That's a different tool. Or maybe your job is to discover something totally new in your data. Let's start with that first job. Okay, let's dive into our first major job, predicting numbers. Now, in the machine learning world, this has a specific name. We call it regression. The goal here is pretty straightforward. We want to predict a specific number, and not just a category like high or low, but an actual number. Like, what will the exact price of this house be, or what will the temperature be tomorrow at noon? To do this, we need to pull out our first set of tools from the toolbox. So let's start with the absolute classic, the simplest tool in the box, linear regression. The analogy here is perfect. Just picture all your data as a bunch of dots on a graph. This model is literally like taking a ruler and trying to draw the one single straight line that best fits through all those dots. It's that simple. And right away, you can see the trade-off, can't you? The best thing about this tool is that it's super fast and incredibly easy to understand. You can look at that line and know exactly how it's making its predictions. But its weakness is right there in the name, linear. If the real pattern in your data has curves and twists and turns, well, a straight ruler just isn't going to get the job done. So what do you do when things get messy? Well, that's when you bring in the heavy hitters, like a random forest. Now, forget about one simple ruler. I want you to imagine you're assembling a committee of hundreds, even thousands of experts. Each expert looks at the problem a little differently, and then they all vote on the final answer. It's the classic wisdom of the crowd, but for data. And this gets us to one of the biggest themes in all of machine learning. With this expert committee, you get amazing accuracy. It can find all those complex, curvy patterns that our simple ruler completely missed. But what's the catch? Well, it can become a bit of a black box. It's much, much harder to ask the committee of 1,000 experts why they decided on that specific number. You're basically trading simplicity for raw power. Okay, so that's predicting numbers. Now, let's switch gears and move on to our second big job, sorting things into different buckets. This is what we call classification. So here, the goal isn't a specific number. It's a label, a category. Is this email spam or not spam? Is this picture a cat or a dog? It's all about making a choice between a few distinct options. Now, a really cool and intuitive tool for this job is called K-nearest neighbors, or KNN for short. And honestly, it works just like you'd expect. If you want to know if someone likes rock music, a pretty good guess is to look at what their closest friends listen to, right? That's all this model does. It finds the K most similar data points, its closest neighbors, and just takes a vote. It's that simple. You gotta love how simple that is. But like any tool, it's got its quirks. Since it has to compare every new thing to everything else in your dataset, it can get really slow if you have a ton of data. And here's a big one. You have to make sure everything is on the same scale. If you're comparing houses by price, a huge number, and number of bedrooms, a tiny number, the price is going to totally overwhelm the calculation, and the number of bedrooms will basically be ignored. Now, this table really gets to the heart of the matter for classification. It shows that same trade-off between accuracy and being able to explain the answer. On one end, you have a single decision tree. It's like a simple game of 20 questions, super easy to follow the logic. In the middle, you have random forest, our expert committee again.
Great accuracy, but a little harder to understand. And then you have the powerhouse, gradient boosting. Think of this like an assembly line of specialists. The first model makes a guess. The next one corrects its mistakes. The next one corrects that one's mistakes. The accuracy can be absolutely top tier, but explaining how it works, good luck with that.
All right, time for our third and final job. Now, this one's a little different from the others. This one is all about discovery. We call it clustering.
So with the first two jobs, we always had a target, right? A correct answer we were trying to guess. With clustering, we don't. We just have a huge pile of data and we turn to the machine and say, hey, are there any natural groups in here? It's the model's job to discover patterns, like finding different kinds of online shoppers, let's say bargain hunters and high-value shoppers, without you ever telling it what those groups should be.
And there are two main ways to think about this. On the left, you have k-means. This is like someone handing you a giant bowl of M&Ms and saying, sort these into exactly 5 piles. You have to tell it the number of groups you want up front. On the right, you have something totally different, like dbScan. This is like looking up at the night sky and finding constellations. You don't tell it how many to find. It just looks for dense clusters of stars. And it can even point out the lonely, isolated stars and call them outliers. Pretty cool, right?
So, we've gone through all the jobs and we've looked at the major tools in our toolbox. Now, let's put it all together into a simple, practical guide you can actually use.
Look, it really comes down to these 4 steps. First, and this is by far the most important, know what your goal is. Are you trying to predict a number, a category, or just find some groups? Second, and please remember this, always start simple. Don't jump to the most complicated, powerful tool right away. A simple model gives you a baseline. Third, you have to consciously make that choice. Do I need the absolute best accuracy possible, or do I need an answer I can actually explain to someone? And finally, you just have to experiment. No guide can replace trying a few different models and seeing what works best for your data.
This leads to a really famous idea in machine learning called the no free lunch theorem. And all it means is that there's no single silver bullet. There's no one model that's the best for every single problem. What works perfectly for one project might be terrible for another. At the end of the day, picking the right model is both a science and a bit of an art.
So there you have it. We've defined the jobs and we've opened up the toolbox. We've seen everything from the simple rulers to the complex expert committees. The only question left is, now that you have the tools, what problem are you going to solve first? Thanks for joining me.